I would be entirely unsurprised if many people came to similar ideas, and then one person presented the thing better, more clearly, or took advantage of the more recent discoveries in order to cause the idea to become more widely accepted.
Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm lucky to be joined by Kerry Vaughan, a program manager at Leverage Research. His work studies early scientific discoveries like electricity. Specifically, he analyzes the history of inventions like the Leyden Jar and the Electrophorus to learn what it takes for inventions to be successful. I'm really excited for our free-ranging conversation today. Thank you so much for taking the time to join me today. I really appreciate this opportunity to just dive through the story here. Before we get all wrapped up in that story, I'd love to hear a little bit about you, plus what you've been up to with Leverage Research.
Sure. So I'm Kerry. I'm in charge of our History of Science research program at Leverage. And that program is trying to go through the history of science, look into how all the major discoveries were made, how especially successful fields progressed, and then use that to gain insights into how struggling or nascent fields of science today might be able to make progress.
Yeah, it's a really unique area of research. I really like especially the case studies that you put out all the time. We'll definitely make sure to link to some of them today. But I guess I'll leave it up to you to introduce some of your recent work and what you've been exploring with electricity.
Sure. We've done a number of different case studies. So we've been focusing on the history of electricity because we think if we can go from the beginning of electricity to the end, which we're considering Maxwell's mathematical synthesis of electricity and magnetism and heat and light, if we can map out how that whole field developed, then the hope is that we'll gain some insights into what does it take for a field to go from pretty rudimentary study of a phenomenon where the details are unclear to something quite sophisticated and that we built tons of modern technology on top of.
I think it's really nice that you're using electricity as a case study because, these days everyone's excited about the cool things with batteries and Teslas and whatnot, but it's also really cool to hear about some of the steampunk inventions, I'll call them, from your case studies.
Yeah. Where electricity started is also kind of fascinating. So we have a case study on Gilbert. So Gilbert was 1600s. He writes a thing called On the Magnet. And one of the main contributions he had to the study of electricity is he distinguished electrical attraction and repulsion from magnetic attraction and repulsion. And the way electrical attraction and repulsion worked in those days is you took amber and you rubbed it. And people noticed that if you rubbed amber, you could pick up light objects. So it was kind of like a curiosity or an oddity. They also noticed that the lodestone would attract iron in particular, usually like small iron filings, because the attraction and repulsion wasn't a very strong effect at that time. And Gilbert's initial contribution was he demonstrates that lots of things attract in the way that amber does. So it's not unique to amber, but lots of things don't attract in the way that magnetism does or the way that the lodestone does. So most objects aren't affected by magnetism. And so he distinguishes those. It was kind of funny to think that we went from a guy rubbing a stone basically and picking up little small objects to computers and Teslas and all of this, amazing electrical developments that we have today.
Yeah, let's actually get into that. So we're talking about the timeline of how things are progressing. Could you talk about more people like Gilbert and the rough years that this case study focuses on?
Sure. We've done case studies a little bit throughout, distributed across the history. So we've got the case study from Gilbert and the distinction of electricity from magnetism. That's 1600s. We completed a case study on the Leyden Jar, which I'm sure we'll talk about, but the Leyden Jar was a development in creating much stronger electric shocks and harnessing more electricity. That happens in the mid-1700s. We also looked into the Electrophorus, which happens like 1775. And then more recently, my colleague Evan Pence is working on a case study on Benjamin Franklin and his contributions to electricity. He was, in his era, he was the guy on electricity. People loved him. They wrote poems about him. The history of how much people were into Franklin, especially as an electrician, is really interesting. And then most recently, I completed a case study on the discovery of electromagnetism. So in 1820, a guy named Oersted discovered that if you run electricity through a wire and put something magnetic near it, the wire affects the thing magnetically, which was the first clear case where you can convert electricity into magnetism. And so I think we'll end up going up until Maxwell, which is, I think, late 1800s, and the kind of mathematical synthesis that combined a bunch of fields in physics together. And then I think Gilbert is going to continue to be the starting point.
Yeah, there's a big range there. Would it be correct to say that some of the core, early time periods there would be with Franklin and the Leyden Jar?
Yeah, essentially electricity starts out as kind of an oddity or curiosity, and there's some research done into what things conduct electricity, for example, and into electric lights, so how to create light from electricity. And that happens kind of early on, but there's not a ton of effort going into electricity in the early periods until the Leyden Jar, which both attracts a bunch of new entrants into the field who become interested in electricity and makes it easier to do experiments on electricity. And that kind of gravitates a ton of attention to electricity, which then leads to quite a lot of further development after that point.
Yeah, so let's talk about it. What is a Leyden Jar?
Yeah, so a Leyden Jar is, so the classic example is take a glass jar and you put kind of a metal coating on the inside of the glass jar and on the outside of the glass jar. And then you attach the outside of the jar to ground. The discovery is made by holding it. And you apply some source of static electricity to a wire that goes through the top of the jar and into some water that's inside it. So initial work with it, we used a medicine bottle, which had a cork stopper, and then you can hammer a nail into it so that it goes into some water. In fact, I have made, when I first started reading about this, made my own Leyden jar by finding a YouTube tutorial and putting some water in a plastic bottle. And, so you can make one of these at home, although be a little bit careful with it. And the way it works is you apply charge to the metal piece that's going into the water while holding it. And then after you're done charging it, if you connect the inside and outside of the Leyden jar together, you get a bright visible spark and a pretty loud pop. And this was a really significant increase in the amount of electric power that people could command. In fact, one of the people who discovered it, named Lusenbrock, he took the shock after one of his assistants made the initial discovery, and he described it as so powerful that he wouldn't do it again for all the Kingdom of France, because he thought he was going to die. The thing was powerful enough. And so the operation of the Leyden jar became a pretty standardized procedure. So it was clear, you need to hold it or attach it to ground. You charge it in these ways. Here's how it functions. So it could reliably produce electric phenomenon, and they were strong. They were visible, interesting, noticeable effect on people. And so kind of a big part of Leyden jar's contribution to the subsequent study of electricity comes from that ability to create an interesting, repeatable, regular phenomenon and the struggle to explain how the heck it is that the thing works, because a number of things about it are quite puzzling. So for example, it appeared initially that you needed to hold the jar, but why on earth why would holding it need to be a part of how electricity functions? And it wasn't at all clear why the spark should be so strong. And there were a number of puzzles. And so the struggle to kind of explain that and the use of that to conduct additional electrical experiments really got the field underway to a much stronger degree than was true before the Leyden jar.
Yeah, and you keep mentioning these words, oddity and electrical experiments. These days, people wouldn't be familiar with what that means. Could you talk about the electrician culture back then?
Yeah, sure. So first of all, scientists thought of themselves as natural philosophers, which is different than the modern conception of scientists, but related. And the culture there was very much, there were few kind of professional natural philosophers. A lot of it was especially wealthy people who had leisure time who were interested in it. In fact, Benjamin Franklin makes probably the most major theoretical advance in electricity when he's nearly retired and he's just kind of, he's having fun doing whatever seems interesting. Electrical studies seemed interesting. That was very much part of the culture. And another big part of the culture was creating electrical amusements or things that would be fun and interesting for your friends. So in his first letter on electricity, he describes this fun kind of prank where he has a picture of the king of England at that time, with a little metallic crown on him. And he's attached the crown to a Leyden jar somehow. And he tells people to come and try and take the crown off the king. They do that, they get a pretty vicious, shock. And it's as though, lightning had struck you down as you tried to remove the crown from the king. And so there was a lot of descriptions of experiments of that type. Other aspects of the culture there's a fair number of traveling electrical demonstrators. So these are kind of lecturers who go from city to city. They have all the latest electrical instruments, and then they kind of perform for audiences. They show them how the instruments work. They explain how they think electricity works. And some number of people made a living doing that, which wasn't otherwise particularly common. It was almost always wealthy elites that would go to these, but that was part of the culture. And then another important part of the culture during this time period is medical electricity. So people thought that the Leyden jar and the Electrophorus might cure various physical ailments that people had. And the evidence suggests that they probably did cure people of various things at some points, unless reports are just straightforwardly lying about what has occurred, which we can't rule out. But they appear to have had some success. Probably it wasn't super repeatable. Probably if we tried to do it again today, it wouldn't succeed. But there was some reason to think that electricity might help cure things. And a number of people set up businesses, put out their shingle to be an electrical healer and use the latest instruments to try and relieve various ailments. All of that was a part of the culture in electricity. And I think the kind of interest in entertainment or demonstrations, I think that seems kind of odd to us today. Could just be a relic of the time period. Could just be that was the culture of the particular time and place that electricians operated. But the more I think about it and the more I look at things today, I see some of that going on even in more recent times. So some examples are take DeepMind's success in beating video games and beating world champions at Go. That's a spectacle that's designed to focus research attention, where you have feedback loops that can tell you whether you're getting better or not. I think in the same way, electricians were producing practical jokes as a way of kind of gaining recognition and having a feedback loop that tells them whether they're mastering the thing under study or not. If you can produce increasingly sophisticated and interesting pranks and practical jokes, you get better at understanding electricity and how it functions. And then even more recently, I've been doing a little bit of light reading about Bell Labs, and Shannon, who is the inventor of information theory, which is a major contribution to our understanding of computation. He spent most of his time building odd contraptions and gadgets. So I think he built a tuba that was supposed to have spit fire and a machine that could juggle. And he built a maze that was electronically configured so that a mouse would run in it. And then somehow the mouse would remember how to do the maze and it would do it again next time. And the commonality there is that these are new fields where the exact way to make progress isn't yet clear. But by following things that seem interesting to you and interesting to other people and trying to master the phenomenon, I think that might be a way to make substantial progress in those kinds of areas. So I think while the kind of show culture and practical joke culture that appears to be there for electricians seems kind of odd, it might turn out to be a reasonably valid research strategy in certain situations.
Yeah. And would it be fair to put it like you had a bunch of full-grown adults that were playing with batteries while trying to figure out how do batteries work?
Yeah, something like that. They were playing around with the Leyden jar, trying to figure out how it worked, how they can make it work stronger or differently, or what have you.
Yeah. And I guess one last framing question. When you talk about time and place, was this just focused on Europe and the US?
Yeah, so the major scientific centers in the mid to late 1700s, early 1800s were definitely Paris and London. And there were also major contributions made from Alessandra Volta, who came from Italy, and from Benjamin Franklin, who came from America. I think Franklin's contribution and his origin in America at that time was something of its own oddity and curiosity. I think they saw him as this kind of plain-spoken guy from out of nowhere, wasn't up to date on the scientific culture of the time. And I think that turned out to be part of his mystique and appeal, was that he seemed like a person who had investigated electricity for himself, learned how it worked, spoke plainly and simply about it. And that turned out to be a major contribution. And that kind of fit the spirit of the Enlightenment that was getting underway at that point.
Yeah, and I know that Franklin becomes, the center of a lot of debate. Could we talk about his early theories and how they related to explaining the Leyden jar?
Sure. So Franklin, some number of years after the Leyden jar, he writes a series of letters that are intended to explain the Leyden jar and explain some of the things that he's been able to do with it. And those letters go on to be very, very successful. He becomes the kind of standard accepted explanation of the Leyden jar. And as I mentioned earlier, people write poetry about him. He's compared to Newton. I mean, he is quite a big deal in the study of electricity. And his account of the Leyden jar, it's kind of worth reading just for yourself, because one of the things that it does so well is it explains the thing clearly, and it kind of embeds itself into your mind in trying to understand it. So when I think about the Leyden jar and how it works today, I know the modern scientific explanation. I think in Franklin's terms, because they're much more useful to me, much easier to use to understand what's going on. And I can make successful predictions about what's going to happen on the basis of that account. And he has a few important kind of innovations in terms of the nomenclature and explanation. So he talks about things being electrified plus or minus. And this is importantly different than the modern conception, where minus is, has more electrons than protons, and positive has more protons. What Franklin has in mind is that objects have a kind of natural amount of electricity, or an equilibrium state. And then you can either add more electricity to an item or to an object, or you can take electricity away. And his explanation of the Leyden jar is that what's going on essentially is you're adding electricity to the inside of the Leyden jar, which then doesn't penetrate the glass. But since electricity is repulsive, that repulses an equal amount away from the outside of the Leyden jar and to ground. And then when you connect them, the reason there's such a violent shock is that there's quite a large difference between inside and outside in terms of how much electricity there is. And it wants to reach equilibrium. So it tries to do that all at once. And that creates the shock, and that creates the spark. People at the time found it to be a very useful explanation. And that's certainly been my experience from reading it.
Yeah. And I can imagine analogies between that and modern, how we might think of like voltage and what you mentioned, deficit and surplus of electrons.
Yeah.
Where does that theory fall short?
So Franklin's theory had some difficulties explaining facts about attraction and repulsion. The most famous case is this problem called the problem of minus repulsion. So on Franklin's theory, an object is charged minus when you remove electricity so that it has less than its normal amount. And the reason that charged objects repulse is that electricity repulses itself. But people found that you can remove electricity from an object, remove electricity from a second object, bring them together, and they'll repulse. But it seems like you removed the thing that's supposed to be causing the repulsion. And so how could the absence of that thing be causing repulsion? And Franklin, a virtue of Franklin as a theorist is he's pretty straightforward that he does not know how to explain this. It's a problem. It doesn't make sense, but he thinks his theory still stands despite that. And people proposed various explanations. One kind of theorist named Aponus proposed that perhaps ordinary matter is also self-repulsive, which we now believe to be the case. But given that we knew that gravity was attractive, it would be quite odd if there was both an attractive and a repulsive force in the same piece of matter that operated differently. There wasn't a way to account for that. So problem of minus repulsion is quite a problem at the time. And then more generally, Franklin has some problems in how he tries to explain attraction and repulsion. And I don't want to get too deep into the 17th century or 18th century theory here, but there's a question of where the electricity resides in a charged object, an object that's charged plus, so it has too much. Is it inside the object? Is it on the surface? Is it in the atmosphere surrounding the object? And that question is largely unresolved. There's good reason to think that it might, in fact, be in the atmosphere around the object because of a phenomenon called the electric spiderweb. So if you bring your hand, especially like the skin of your forearm, if you've got hair on your forearm, near a charged object, you get like a tingly sensation that people liken to kind of having run your hand through a spider web. And so several theorists were like, okay, well, that means the electricity is there. It's interacting with your skin. That's why you get that effect. And the problem is, if there's an electrical atmosphere, you need to explain how attraction and repulsion works. Some people following Franklin thought that there was a transfer of electricity between electric atmospheres, and that explained it. But in any case, this question of where does the electricity reside and Franklin's answer to it leads to some theoretical contradictions and problems for Franklin's theory. And then it takes Volta's invention of the Electrophorus before people seriously grapple with those questions, and that gets resolved.
All right, let's talk about that. So what is a Volta and an Electrophorus?
Sure. So Volta is Alessandra Volta, who's the Italian natural philosopher who discovered both the Electrophorus, and then also he discovered the voltaic pile, which is a precursor to the battery. You can buy a replica of an Electrophorus just on Amazon, which is what I did to do some getting a sense of how the thing worked. And the way an Electrophorus works is you've got a non-conductive material. and rub it or put static electricity on it somehow. Rubbing it usually is sufficient. And then you take a metal plate with a conductive handle on it, and you can put it on the material that's insulated that now has some electric charge on it. And then you can touch the top of the plate, which gets a small spark, take it off, touch it to something else, which generates another spark. And then you can just repeat this process. So you take the metal off, touch it somewhere, put it on, touch it, take it off, touch it somewhere, put it on, over and over and over again. And you can use this to, for example, charge a Leyden jar itself and get a pretty large shock. And the thing that was interesting there is, where is the electricity coming from? It seemed like you can just repeat this process over and over and over and over again, even though you rubbed the surface of the non-conductive material once. And that was quite an interesting phenomenon, quite a thing to explain. And one of the things that it suggested to electricians eventually was that the electricity that's being generated by the Electrophorus isn't coming from the non-conductive material itself. The Electrophorus is difficult to communicate abstractly in words. So for people who are interested, I'd recommend you search for YouTube videos of it. And then my paper, I have like a step-by-step, this, you do this, you do this, you do this, that explains exactly how it works using a modern replica. But it was like a really interesting invention that helped people understand how attraction and repulsion work in electricity.
Yeah, and I know a lot of your research focused on uniquely analyzing Volta's intentions about making this device simple and making it easy for people to use. Could you talk about why you decided to focus on analyzing Volta's intentions like that?
Sure. So one of the things I found while doing initial research on Volta and the Electrophorus was that kind of really interesting, you get the sparks over and over again phenomenon was not first demonstrated by Volta. And so Volta now is pretty famous, but at the time, Volta was kind of an unknown. He was just starting out as a natural philosopher. He had written some letters to well-known natural philosophers, and like one of them had a sufficiently positive thing to say. So he's an unknown just starting out his career. And two very famous natural philosophers named Beccaria and Wilkie had treatises that were pretty widely read where they demonstrate this phenomenon. They demonstrate this repeated sparks phenomenon in those treatises. And so the question I was immediately intrigued by is, why did Volta's thing become quite famous and well-known and appear to be the thing that changed how people thought about attraction and repulsion, whereas these much more famous natural philosophers who demonstrated the phenomena first didn't? And the explanation that I ended up coming to is that Volta designed the Electrophorus in part to ensure that it got distribution. This makes sense generally because he's a young up-and-coming natural philosopher. He wants to make a name for himself. But then also you can see this in various aspects in how Volta designed his device. So, for example, the basic function of the device and how it works is quite simply described by Volta and is pretty simple to interpret by other natural philosophers. So Volta has like a more complex Electrophorus in mind in his initial description. But the core element is you need an insulated material, something metal with an insulated handle. And a bunch of natural philosophers were able to just make their own Electrophorus from reading Volta's description. The most common solution was put some wax on a glass pane, put a handle on a piece of metal, and you're good to go. And so because the thing was simple and therefore easy to imitate, lots of people read Volta's description or read secondhand accounts, made their own and experimented with it. And if you want to cause people to be interested in a puzzle, which is what the Electrophorus was, letting people do it themselves is a much better way to get people interested in that puzzle than reading an abstract description alone. Volta also took some steps to pretty clearly design the device to be used by the kind of traveling electrical showmen and lecturers. He actually designs the device so that it has this like hollow base where you could hold paraphernalia that an electrician might need when they're doing their lectures. So you could take your Electrophorus, it had all the other things that you might need, you bring it into your lecture hall or whatever, and you're ready to go. So that shows that he's trying to use this existing distribution network, which is people doing electrical shows, to kind of get his device out there and have it be interacted with by other natural philosophers and by the public. And then finally, he also has in mind a bunch of medical uses for the Electrophorus. He has designs on building really large ones that would be easier to operate and work more frequently. So he takes a number of steps to cause his device to get adopted, and it appears that he succeeds. And that's why his device becomes well known, and people that have demonstrated the same phenomenon earlier, their innovations are substantially less well known. And the hope is that by studying cases like this, we might in the future be able to figure out what are the elements that are required in order for scientific discovery to gain uptake with the scientific community. Because I think the kind of naive public conception is that that's an automatic process. If the thing's good enough, people will understand it and there'll be uptake. And then I would be a bit surprised if the history turned out to suggest that. I would be entirely unsurprised if many people came to similar ideas and then one person presented the thing better, more clearly, or took advantage of the more recent discoveries in order to cause the idea to become more widely accepted. So that's the kind of hope in studying cases like that, is that we can start to develop what are the things that are required.
Yeah. And I know we're speculating here, but if you could outline like some of your intuitions or hypotheses, which other inventions throughout history might you want to analyze to figure out, well, was it the case that many people got there, but one person presented it better?
Yeah, that's a good question. The most obvious case is going to be Franklin's theory of electricity itself, actually. So my colleague Evan Pence is currently working on a case study specifically on Franklin. And one of the early results from his case study is he was able to find older theorists who had theories that are, in some abstract sense, the same as Franklin's or very similar to Franklin's. They have the same conceptual innovations that Franklin has. And if you asked electricians after Franklin who those guys were, they'd be like, I don't know. I've heard of Franklin, but I haven't heard of those guys. And so one of the things he's trying to explain is, why did Franklin's theory take off to the degree that it did? And going to be a bunch of interesting elements there. There's going to be something that we're still working on how to describe about how easy Franklin's theory is to use cognitively. It's sort of simple and easy to operate with. There's going to be the fact that Franklin's theory came after the Leyden Jar, which was very helpful, because the Leyden Jar attracted a lot of attention and people were very interested in explaining it. I think the way these cases will unfold is we'll find a case of a major innovation, we'll look into the history in detail, and then we'll find people who don't get discussed much at all, who had things that are conceptually and importantly similar. So it's hard to say in the abstract, where will we find this? Because the people who did it before are usually forgotten. But I think we'll be able to find more cases and then describe what was different about the approaches that succeeded versus those that didn't.
Yeah. And this is a question about what I'm not hearing rather than what I am hearing. So I hear you talking about like people's differences in how they communicate and how they create their contraptions so that they can be reused. But a lot of other times where you see historical documentaries or reports about inventions, there's a lot of focus on like the business models and how one company or organization got together and they allowed that to scale. Is there a reason why that's not as prominent in these case studies?
Yeah, I don't know exactly when historically this becomes more common, but we certainly see a development towards industrial research labs that are, for industry, for businesses doing research, which they're hoping to monetize. Bell Labs is a great case of this. There are, of course, others. And that isn't a thing that appears to be what we see in this time period. We do see people setting up businesses related to electrical study. There's several people who are instrument makers, and they sell those instruments to electricians who want to do experiments. But that kind of like industry focus on science and technology it doesn't appear to be as largely prevalent, certainly in the time periods we've studied. I think this is in large part because electricity was not a super useful invention yet or a super useful discovery yet. There wasn't a ton that would be practically useful that you could do with it during this time period, with the exception of the potential to have medical uses. And so I think that's probably why we haven't seen that so far. I guess that we'd see different things in other areas. It is also notable, though, that the magnet did have quite I don't know if it was industrial in that way, but the magnet enabled seafaring in ways that were not possible before. And that was actually quite a major discovery. But for electricity specifically, outside of electrical shows, medical uses, this isn't a thing that businesses are taking advantage of.
Yeah. And to talk a little bit more about your goals, so how you refer to wanting to understand, what works so we can replicate it. Again, same question. What do you think are some areas currently where we have things out there, but maybe they're not being presented in the best way? Maybe you think that the lessons can be applied to.
I can give kind of an example. So around leverage, we've had this theory or this hypothesis, which we call premature mathematization. So the idea is, if you look back in the history of science, the person who kind of did the most serious advanced mathematical work in clarifying an area is Newton early on. And he occurs pretty early relative to the history, the late 1600s, essentially. And what we expect to find is a large number of people with the following idea. I should do for my field what Newton did for celestial mechanics, meaning I should mathematize it, figure out the regularities, come up with these beautiful, elegant equations that describe it, and then that will put the field on firm footing. That will be my decisive contribution. And what we expect to find is a bunch of cases where people tried that and failed, because we know that electricity wasn't highly mathematized until at least the early 1800s, essentially, and I think wasn't on anywhere close to the footing that Newton put celestial mechanics on until mid to late 1800s. And so one of the things that we're hoping to find is we'll find cases where that was tried and wasn't largely successful. And then we may be able to describe, okay, what did those people not have that they later had when the field was successfully mathematized? Was it instruments that can measure the thing precisely enough? Was it the right mathematical equations that could describe the phenomenon? Was it something else? And so we're hoping so you could then build a theory, okay, at what stage in the development of an area of study can it be successfully converted into a highly mathematical area? And one of the really interesting results from a case study I just completed on Oersted and the discovery of electromagnetism is a potential case of premature mathematization. So there we have a kind of approach to science that was popular in France between Napoleon's rise in 1799 and around 1815. And they tried to study the voltaic pile, which is a precursor to the modern battery. And what they ended up doing is they had tools and mathematical techniques to describe a particular way that the voltaic pile operated. And they thought that would just generalize to other ways that it operated. And that generalization turned out to be wrong. So otherwise quite famous French scientists made claims about the pile and how it worked that if you've experimented with the pile in one of its configurations, are just clearly false. Like I can do experiments with a rudimentary thing and see that those claims aren't true. They were true of only a particular way that the pile worked. And so that was an area where they appeared to have prematurely tried to use the mathematical tools and the measurement techniques that they had to do study in that area, and that didn't succeed. And so we're expecting that we'll go back through the history and we'll find other cases that are similar to that case. And then we'll be able to build an account of what do you need in order to mathematize your field. And then that might be helpful because a bunch of the clearly successful fields are highly mathematized. Modern particle physics is clearly quite successful. I think economics has the reputation of being highly successful. And we expect that probably a large number of scientists and scientific fields are trying to imitate that by mathematizing their area now. And they might not be ready. They might not have the tools that they need in order to accomplish that. And so if we could guide them towards, here's what, when physics got going, here's what they actually did. They got them to the place where they could mathematize it. Then that might be helpful for encouraging progress in kind of nascent areas where less progress has been made so far.
Yeah, and economics is like a bit of an oddity thrown into this discussion.
Yeah.
Still controversial, still halfway in the process.
Yeah, I totally agree.
So one thing that intrigues me here is you keep mentioning all of these skills that you're working on, like analyzing the rationale behind an argument, like understanding the raw physics of what's going on, like analyzing, is this information presented in a way that's easy to understand? Are you just a genius, or is there a big team that is working on all of these concepts with their own special strengths?
Yeah, definitely not. So my background is I have a PhD in philosophy. Our executive director also has a PhD in philosophy. I think something about Leverage's approach to studying these certainly involves using philosophical tools to figure out what the arguments are, figure out, do things kind of at that abstract philosophical level. But then also I just have a background of being kind of a generalist. Before I was doing history of science research at Leverage, I was doing community building in the effective altruism community. And then before that, I was working at a foundation. And before that, I was a professional poker player for a little bit. And so the skill of learning the new areas that you need to know is a skill that I've had a chance to pick up over time. And then the other thing that I think is important about Leverage's approach is, so one way that we think about in areas where less progress is being made in science, how much you divide up the areas to look into. And I think it's going to turn out that there are technical, social, and institutional bottlenecks. And we aren't trying to solve the technical bottlenecks necessarily ourselves. We expect that scientific community is doing good work there. But we're very interested in the social and institutional bottlenecks to progress. And so by looking at some of those social factors in particular, which have occurred so far in our case studies, I think that allows us to reach some insights that wouldn't ordinarily be found if we didn't have that kind of lens to the study.
Yeah, and then I assume it is the case that it is just you sitting down for a month and, anything that you need to learn, you will go and learn. It's not like, one psychologist, one philosopher, one physicist all get together.
Yeah. I mean, for the case studies that I've been doing themselves, first of all, it takes a lot longer than a month. But also, in a bunch of cases, I've been able to buy the instruments, essentially, or figure out how to construct them so that I can run experiments with the instruments themselves. That's been extraordinarily helpful. And then one thing that's really great about studying the history of science is the physics is the same, right? The physics works the same way now as it did then, which isn't true for a lot of more thoroughly social phenomenon, which, where the social effects could have been quite different in the past as now. And so in many cases, we can use advances that have occurred in physics since the discoveries were made to work out exactly what the experimenters could have seen and couldn't have seen, and exactly what might have been going on. So as an example, in the Ørsted case study, so the thing Ørsted discovered was that if you run a current through a wire, it can deflect a magnetic compass needle. One of the questions I initially started with was, okay, when could that discovery have been made? Could it have been made substantially before Ørsted? Could it have been made only recently? Because knowing that will tell you, what do I have to explain about Ørsted's discovery? Do I need to explain why he got there first? Or I need to explain why he made a major conceptual innovation? And what I was able to discover is that the things you need to produce a magnetic effect, like the type Ørsted observed, is you need enough current going through a wire, you need a detector of magnetism, and then you need to configure your detector and the current in the right way so that you can detect the effect. And then we were able to read descriptions of experiments that scientists performed and just work out how much current they had. We read an experiment from 1802 where the scientist runs current through an iron wire that's 1/10 of an inch thick. And subsequent developments led to equations that will tell you how much current you need to melt iron 1/10 of an inch thick. And so we were able to work out that requires 100 amps to melt that wire. And then we were able to use equations that describe the magnetic field around a wire that's carrying an electric current. You can work out how strong that field is depending on the amount of current that's going through the wire and how close you are to the wire. And so with that, we were able to work out, okay, how much current did they need to produce a detectable effect? And the answer is somewhere in the 1 to 10 amps range. So they produced 1 or 2 orders of magnitude more current than they needed. And that lets us show that discovery could have been made by 1802. And that's just unique to the history of science because the things they are studying are regularities that we've made subsequent progress on. And so you can just work out exactly what they were able to demonstrate and what not. And you can use that to kind of come to more precise conclusions than might be possible in other kinds of areas.
Yeah. And on that note, it seems like you're digging a lot in terms of you're going back so far into the past and trying to find sources for all this. Where do you find all this information?
Yeah. So a lot of it is, for the Ørsted case study in particular, there's just a lot of good primary source information. Google Books just has a bunch of the journals and Internet Archive does, and you can just go read the original experimental reports. In some areas, there's good secondary literature that points to interesting problems, but a combination of the secondary literature that kind of gives the current historian's sense of the area, plus reading primary sources, plus speculating with each other to try and figure out what could possibly be going on here is kind of the approach that we've taken so far.
And are the primary sources actual published journals? Was that institution? Okay.
Yeah. So there's different journals, different availability in different languages. But in English, there's the Proceedings of the Royal Society, which go back very far into the history. And the Royal Society was a well-respected institution. It kind of tells you what people were most interested in or what the kind of cutting edge of research was. And then also in the kind of late 1700s, early 1800s, there's quite a rise of independent journals where some reasonably well-known natural philosopher will set up a journal, start taking submissions, start publishing it. And For the time periods that I've been studying, that just contains tons and tons of experimental reports and interesting findings. And it covers what's going on in other scientific centers that aren't produced in English, which makes it easier, for me to get access to. So usefully, there's a lot of information there. And this is, again, a nice thing about studying the history of science is scientists are trying to make it very clear what they did and what discovery they made and how it worked, because that's part of scientific practice, is trying to make it as clear as possible so that other people can follow along. And so, even me, hundreds of years later, I can follow what they were doing and how it worked and so on.
Yeah, that's really interesting how it's very unique to that Enlightenment age culture. It's always an interesting question to ponder, okay, if this is happening in this part of the world, then what's going on everywhere else that we don't have a record of? There's lots of cool stuff that you're doing at Leverage Research. What do you think are some of the directions you're heading in the future with this approach?
Sure. So in general, for Leverage, there's a few areas we're heading in. One is we recently ran a kind of workshop on scientific bottlenecks. So we picked 10 areas where we thought progress could be made. If progress was made, it'd be beneficial to humanity, and where we thought there would be bottlenecks to progress that could be uncovered. Found experts who both understood the technical details of those fields, but also could look at the social and institutional factors that might be causing the bottlenecks. And then we invited a bunch of funders like Peter Thiel and Patrick Collison and lots of people who were interested in seeing scientific progress occur. And we had the experts give reports on what they thought the bottlenecks were in various areas. And so that's a really exciting initiative. The response to that has been overwhelmingly positive, and so I expect we'll continue that into the future. And then a thing that I'm kind of interested in personally that's kind of outside of the case studies is I'm very interested in the idea of responsible scientific advance. So I think science is the greatest institution of knowledge generation that has ever existed, arguably, and is responsible for dramatic increases in wealth and prosperity today. But it also seems that increasingly, as scientific progress continues, the odds that a discovery will cause untold catastrophe seems to increase. There's obvious cases like the building of the atomic bomb, which plausibly could have wiped out a very large percentage of all people had governments decided to use that differently. There's artificial general intelligence, which a bunch of people are concerned about. And in the news more recently, there's gain of function research, for example, which might have produced a very deadly pandemic. And part of what I'm interested in is it seems that scientific culture is knowledge maximizing. So they will go out and acquire the knowledge if there's knowledge to be gained, kind of in the way that businesses are profit maximizing. And just as businesses are profit maximizing in a way that might be harmful to society, my concern is scientific culture might be knowledge maximizing in a way that could be harmful to society. So I'm interested in whether that hypothesis is true. And if so, what could we do with scientific institutions so that scientists don't go out and acquire knowledge that could be catastrophically harmful?
And how is that different from, let's say, obvious cases like in World War II, horrible things done? I'm thinking of Japanese experiments being run and people develop some ethical guidelines. You're saying there's more to it than that?
Yeah. So I think society has done, I don't want to say a good job, but society has addressed the problem of scientific experimentation leading to harm to vulnerable populations of people. And so the history of this is pretty horrible to read about, but there's CIA experimentations, there's Nazi experimentations on people, there's giving people syphilis and seeing what would happen. There's a history of quite clear violations of any reasonable ethical guidelines in the past. And as far as I can tell, and I've only done preliminary research into this, but as far as I can tell, society responded by creating ways of policing the ethics of these kinds of experiments. So ethics review boards at hospitals or that have to deal with experiments on human subjects seem to be an example of this. And the solution they arrived at there was a mix of scientific and non-scientific oversight. So it's common to have priests and philosophers on these committees who kind of oversee whether experiments should occur. And I haven't personally interacted with these, but from reports I've read of others, I don't want to say they're doing a good job. It's hard to say, but they create a lot of red tape. It's hard to run experiments. The rules don't really make sense to anybody who's trying to look at whether the rules do in fact make sense. But that is a case where by imposing this kind of system, it probably does help ensure that we don't use scientific experimentation to cause harm to vulnerable populations. I think the question of how do you ensure that scientific experimentation doesn't lead to uncovering dramatically bad new knowledge, I think is going to require different approaches probably, because you don't know exactly what you're going to find until you find it. And so it's hard to have a review board of non-scientists also, with any kind of information, predict what you're going to find. So the ideal solution is that the scientific community itself governs this in the way that the scientific community governs most other aspects of science. But the concern is that that's not a function that the scientific community sees itself as serving now. And so if all of that's right, then figuring out why is that and how can the culture of scientific practice be changed is something that I'm interested in. And I think interested in particular because we don't know whether the coronavirus pandemic was the result of any kind of lab escape or anything like that. We don't know whether that was a result of scientific experimentation, but pretty plausible that it could have. It's certainly not an insane hypothesis. And that alone is quite scary to me. It's not an insane hypothesis that scientific research could have led to the deaths of millions of people. Like, we shouldn't be in a world in which that's not an insane hypothesis.
Yeah, it's amazing to hear all the big questions you are asking. I think there's a lot of exciting work to come out of Leverage. To wrap up, what are some ways people can learn more about your work?
Sure. So you can go to leverageresearch.org. We've got all of our case studies, all the things we're working on there.
That sounds great. I'll be sure to link to those things, plus add some other links to the concepts we've been mentioning throughout. And I really do appreciate you sharing all of these big questions you're asking and your hypotheses for what is the knowledge we need to acquire as a species.
Yeah, thanks. I appreciate it. It's been fun.